Hello. In the previous lecture, we introduced the idea of a transformation. And today we will look at Fourier transform. Now, it will not be a proper mathematical treatment because this would take quite a few lectures. Instead, I'm going to tell you a story about Fourier transform with some mathematics thrown in. And I'm not really feeling bad about it because the Fourier transform is actually not the transform that we want in this course. But still, I think I should tell you the story because it's a nice story. Fourier transform is useful, and it's a direct inspiration for the transform that we want, that we will see in the next lecture. So let's start. And I will start with sort of like a general story about sciences. In sciences, one of the key questions is studying dependency of different quantities, how one quantity depends on another. And we use functions to describe such dependencies, how one variable depends on another. We can visualize it easily by looking at graphs of functions. So instead of functions, we can also think of shapes. And there are many possible dependencies, many possible shapes. However, some of them are not all that convenient to work with. On the other hand, there are some functions or shapes that are really, really pleasant. For instance, powers. X to power 0 is just 1. Then there is x, x squared, x cubed, x to power 4, and so on. Now, arguably, these are the most convenient functions to work with. They can be easily evaluated. In fact, they are, I think, the only functions that can be evaluated directly. They can be easily differentiated, integrated. We know how the graphs look like. So these are really luxurious functions. Unfortunately, there's just few of them. Their shapes are very specific, and there are dependencies which are different. So we need to somehow extend our range of possibilities. And for that, we will first look at linear algebra. And we imagine that these powers are in fact vectors in a space of all functions. And it's not difficult to check that they are linearly independent. So they form a basis of some subspace. And when you have a basis in linear algebra, it is quite natural to take linear combinations. So how does a linear combination look like? Well, you pick some of the vectors in your basis, you multiply them by constants, and you sum them up. Let's say I pick 1 and multiply it by, for instance, 13. Then I pick x squared multiplied by 5. And then I pick x cubed and I multiply it by -4. And that's a linear combination of my basis. And it's a polynomial. So when we talk about linear algebra, about linear combinations and powers, we are in fact talking about the world of polynomials, and this one is quite rich. It's very rich, and there are many dependencies that can be described using polynomials. However, that's still not enough. This is a rich family, but there are some shapes which are outside of this family. For instance, this one. I'm pretty sure that you know it. I'm suggesting here that this is the sine function. And this is where it gets interesting. Polynomials are finite linear combinations of my basic functions, of my powers. So let's step out of the world of linear algebra and start thinking about infinite linear combinations. Once you start thinking about infinite linear combinations, suddenly there is a way of describing this familiar shape, and it looks like this. It's x minus x cubed over 3 factorial plus x to power 5 over 5 factorial minus x to power 7 over 7 factorial plus, and so on. We keep going. Now, of course, that's the famous Taylor expansion for the sine function. And one has to develop a theory so that this makes sense, infinite polynomials. Of course, we call them power series, and there is a theory, and presumably you heard about it in your calculus class. So the basic idea is that you have a world of shapes, and you're trying to enrich it by passing from finite polynomials or finite linear combinations to infinite linear combinations. You have to develop theory. And then you are in a situation when you have a function, and you may replace it by an infinite polynomial, so to speak. Now, I'm not speaking as a mathematician now. That's why it's a storytelling. As a mathematician, I should be talking about power series, centered at origin, for instance. And I talked about it previously, that this, in fact, gives rise to a transformation. But let's talk about a little bit about the analytic part of it, the calculus part. So what are the chances that when you are given a shape, a dependency, a function, you can express it using an infinite polynomial? Well, there is some theory, and there is an interesting outcome from the theory, and it says, okay, if you can express your function as an infinite polynomial, then you don't really have much choice. There's only one type of coefficients that will work for you. ak is equal to the kth derivative of f at 0 divided by k factorial. That's something that is known quite well. But it's information which only goes one way. It goes, if you have this series expansion, then your coefficients look like this. It doesn't go the other way around. So when you have a function, perhaps it's nice. It has all the derivatives. So you can form these coefficients, you can calculate them, and then use these coefficients to form a series. And the question is, okay, you have a series, you have a function. Are they equal? Is it the same? And the answer is not always. And this is unpleasant. So there is a chain. You have a function. You find coefficients. And this is the first little question mark, because for some functions you cannot find the coefficients if they don't have the derivatives. And then the next question mark, and that's a big question mark, is whether f is equal to the summation akx to k. So that's a general picture. And there are some theorems which tell you that if f is really nice, then definitely you can express it as a Taylor series. But I don't want to go into details too much. I just want to see the general picture. What the theorem, the one which I quoted here, does for us is it tells us that it's absolutely pointless to try to find series expansion in any other way. This is the only candidate. You simply have to try these guys, and if they work, you're fine. If they don't work, then you know that there is no expansion possible. There's no other way. Okay? Now, we will try to mimic this in a slightly different world, but to appreciate it, we still have to do a little bit of review of calculus. And again, I'm not going to go into theory, into mathematics too much. I will tell you a story a little bit. So I will just remind you of things that hopefully you know. Probably the easiest series expansion looks like this. So formally, this is a summation k ranging from 0 to infinity, x to the power k. When I write an equality like that, what does it really mean? Well, first of all, formally, this is taken so-called locally. I have a function here, and we actually know how it looks like. And to be precise, I should specify where this expansion is valid, because it's not valid everywhere. So let me just focus on the interval between 0 and 1. One is open. One has to be open, otherwise I'm in trouble here. This expansion is also valid for small negative numbers, but I'm not going to be all that interested in that. So there is a function 1 over 1 minus x, and I know how it looks like on this interval. It's actually a part of a hyperbola. So here is 0, here is 1, and at 1 we have a vertical asymptote, and the function goes like that. And now the basic function series theory tells us that if you want to have a function and a series of functions, an equality between them, then the interpretation is, above all, local. So you pick some number, let's say 0.3, and you put it here, and you also put it here. And when you put a number 0.3 for x, it becomes a series of numbers. And we have a theory for a series of numbers. We know how to handle it. We go to partial sums. So we essentially form finite sums, and we look at the outcomes. So here is 0.3, and here is the value of my function when I put 0.3 into this. And now I'm putting 0.3 here and taking finite sums, partial sums, and I'm getting numbers, and they should be getting closer and closer and closer to this target. So I should be approaching it from, perhaps from below, like that. Then I pick another number, and again I look at my target on the left, and then I take this number, put it here for x, and again that's a series of real numbers, so I look at partial sums, and I'm getting some partial results, some numbers which hopefully approach this guy, and they do, okay? Because when you're looking at it like that, so-called pointwise convergence, then this is nothing else but the famous formula for the sum of a geometric sequence, okay? And this is how convergence is done also for functions. When you have a function on an interval and a power series or some other series of functions, you just look at all the possible x's and you check whether things work. Unfortunately, this is not enough for practical applications because, and that's the key, when you are checking things locally, you have no control over the speed of convergence. It may easily happen that at one place, the convergence of the series is quite fast, but at another place it's very slow. And that's very unpleasant. And to see that, we have to make a global step. We have to look at things globally over the whole interval. So what do I see here? I no longer see different numbers put into x. I just see x to k. That's a function. And how about partial sums? Well, partial sums go like that. You start with k equals 0. X to 0, that's just function 1. We know how it looks like. That's a constant function. Then you take k going from 0 to 1. And that's a linear function. We know how it looks like. It's a shifted diagonal. And then you go k from 0 to 2. That's a parabola. And then you go to 3. And that's a cubic curve, and so on. You keep going. Now, these are functions. They all exist on the interval 0, 1, so I can draw them in, and I can check whether those functions, whether the graphs, as units, as objects, whether they actually approach the graph of the target function. And I'm looking at it globally. So what I want to see is this. If I get some tolerance, then there is a function in my list of partial sums which fits with my target function within this tolerance. And if that happens, then we say that the convergence is uniform, because it means that all those little local convergences go at the same speed, roughly, go uniformly. And this is what we want in applications, and that's what we actually want here in this theorem, when we are inquiring about the shape of the coefficients. Uniform convergence is needed there. Now, this example is interesting in that this convergence is not uniform on the interval 0, 1, because there is a trouble near 1. You know that the function 1 over 1 minus x has a vertical asymptote. It goes to infinity. So when you're looking at things locally, and you are going closer to 1, then it's much harder for these partial sums to actually achieve the target. So when you want to approximate this function 1 over 1 minus x with this precision, then it creates a strip. And then you look at these partial sums, at the polynomials of different length, like that, and you find that each of them, perhaps at the start, lies in this strip, but then it goes away as you near 1. And this is very unpleasant. In applications, it means you couldn't really work with such an expansion on the interval 0, 1. For instance, if you want to differentiate here, you are not allowed to differentiate the series instead, if the convergence is not uniform. Let me show you something. So what we have here is a picture which is not scaled properly. You can see that on the horizontal axis, it's the interval 0, 1. But on the vertical axis, we go from 0 all the way to 20. So it's squeezed like that so that we can see the picture better. The dark blue curve, which is the one on the top, that's the graph of the function 1 over 1 minus x. Let's have a look at the other guys. The red curve, that's the Taylor polynomial of degree 3. So in fact, that's this one. And you can see that when you are near 0, it's actually a fairly good approximation for our target function. We actually cannot see the difference. But as we are getting close to 1, the approximation is getting worse and worse and worse. So we try a longer partial sum. The golden curve, this is the Taylor polynomial of degree 13. So we go all the way to x to 13. And again, you can see that it's close to the target function at the start. And you can also see that the area where the approximation is good got larger. It extended more to the right. But eventually, when we go near enough 1, the approximation becomes really bad. And finally, the same thing is happening with the green curve, which is Taylor polynomial of degree 23, I believe. 23. And that's a problem. Let me show you a little animation. Hopefully, it will show up quickly. Yep, here it is. So again, the dark blue curve, that's exactly the function 1 over 1 minus x. And the red curve, that's at this moment polynomial of degree 1, I believe. So it's this one. And then the animation will pass quickly through something like 20 other polynomials. Here we go. And you can see how things are getting nice. And at this moment, one would perhaps say that now the approximation is really good, but that's because we do not see what's happening near 1. The picture just blows up. You know that there is a vertical asymptote, so it actually goes to infinity. So if I extend the picture, we would see that things are not really good, even for the polynomial of degree 20, which is what we saw with the green curve. So we do not have uniform convergence here. Just out of curiosity, if I cut away 1 and look at smaller interval, then we will have uniform continuity. So on smaller intervals, I could do differentiation and integration and things like that. So this expansion is in fact quite useful. It's not bad. Just we have to avoid this part. Perhaps I should do something over here. Let me change the scale from 0,1 to 0.5. And then I can also show just a smaller part of the y-axis. Here we go. And now, when I run this animation, you will see that the convergence will be uniform because now we see the whole graph. It doesn't extend to infinity. The blue curve, that's exactly the function 1 over 1 minus x on the interval 0.5. And we have a very nice approximation on the whole interval 0.5. So this is uniform convergence. Things are really nice. That's the introductory story. And now we start a new one. Imagine that you have a function that looks like this. There is a basic shape. And this shape is now repeated over and over, so the function is periodic. Perhaps I can make it like that, so that it's easier to draw. So here is another copy of my shape. And here is another copy of my shape, and so on. I will make 3 dots here. And of course, the same thing is happening on the left. And the way I draw it, the basic period is over here. And let's say that it's t. But every time you have a t-periodic function, you can simply consider another chunk of this shape of length t, and it will also serve as a period. So for instance, if I start at 0, which is traditional, and I extend to the right by t, I will see this shape, and again this shape is repeated, it's replicated. So indeed, when you have a t-periodic function, then it doesn't really matter which part of it you consider to be the basic shape. The important thing is that it's interval of length t in this case for a t-periodic function. Let's call it f. And now I have a shape. I want to express it, I want to work with it. And perhaps I would like to express it using functions that I like, which is polynomials. So can I somehow create a Taylor expansion, a power series, which exactly fits this shape? And in fact, the chances are very small. However, when you are thinking about periodic functions, you may think of some other family of functions that are also nice. They are easy to draw, they are easier to differentiate, they are easy to integrate, and they are periodic. And of course, I'm talking about sine and cosine. Let's have a look at sine. Here is the sine function, the basic period, between 0 and 2 pi. Now, when you think about it, there is probably very little chance that you could use functions with periods 2 pi and somehow mix them up and obtain a function with period t which is different, it seems, from the picture. So the key trick here is to scale the sine function and the cosine function so that the period fits. So what I do, I look at the period t, which goes all the way here. And in this particular case, I would have to squeeze the sine function. But sometimes perhaps I would need to extend it. So I want to make a copy of the sine function which oscillates faster. So it should have a higher frequency. And this is done by taking sine and multiplying the variable by some constant omega. If omega is larger than 1, then the sine function oscillates faster, higher frequency. So I would say this is roughly half of the original period. So this would be like sine 2t. Sine 2t oscillates twice as fast. Okay? The same goes with cosine. If you take sine 1/2 of t, then it oscillates slower, and you would have the basic period extending over here. hills like that. That would be sine 1/2 of t. Anyway, now the periods fit, and the question is, what should the omega be, the basic frequency that we will need? Well, let's think about it. I'm substituting a number t into my function, into this function, into this function. That's my important moment, t and 0. When I'm substituting t here, I get omega t, and this is a number inside sine which is supposed to make it 0. And it's supposed to be the second 0 in the row, second 0 in the row. So this argument, omega t, should be 2 pi. And from here, we can see that omega is 2 pi over t. So when I take sine with this frequency, with this omega t, it will be a function which is periodic with period capital T. So it fits, at least with the period length, with my original function f. And of course, the same will work with cosine. So I have two interesting functions, cosine omega t and sine omega t. But now, here is where it gets interesting, because with just two functions, I have little chance of actually composing some shape. I mean, what are the linear combinations of these two functions? You just multiply them, sum them up, one basic shape essentially that you can get. But if I take this omega and I multiply it by 2, I'm increasing the frequency by 2, and there will be still another copy of sine, which will be oscillating twice as fast. Now this copy of sine, let me put it here, sine of 2 omega t. This one actually has a period t divided by 2, the basic period. But if it has a basic period t divided by 2, then it's also automatically t periodic, because this double wave is then repeated over and over. The same thing goes for cosine. And now there is nothing special about number 2, apart from the fact that it's integer, and that's important. So I can also think of cosine 3 omega t and sine 3 omega t. And I can keep going. And I get a family of functions, and this family of functions is infinite. So there is lots of shapes that are suddenly available to me, and I can use them, I can compose them together, and hope to achieve the same shape as this function f. There is one more number which can be put over here, which is 0. 0 is an integer too, not a natural number. If I put 0 into cosine as a multiple, I get sine of 0, which is 0. This is not interesting. But if I put it here, I get cosine of 0 is 1. And that's a useful function in the mix. Because remember, I want to make linear combination of my basic functions. So I'm making linear combinations of these guys, and they are all relatively small. For instance, at the origin, sines are all 0. And perhaps I have some shape which is floating above the x-axis up there, so it may be useful to have 1 as a constant function, which allows me to shift things up globally. So these are so-called trigonometric functions that I need for this given guy f. Everything is hidden in the frequency omega. With this frequency omega, this family fits with my function, not with the shape, but with the length of the period. And now I'm going to form linear combinations of these guys, and I can call them trigonometric polynomials. Just like here we called them polynomials, here I'm going to call them trigonometric polynomials. And then I can ask about infinite polynomials, infinite trigonometric polynomials, and this will be called trigonometric series. And a trigonometric series looks like this. First, let me start with these guys. There is a common way to write them. So it will be cosine k omega t and sine k omega t. And k ranges between 1 and infinity. So these are cosine sines, and I'm forming a linear combination. ak cosine plus bk sine. And then I'm summing up through different k's. So I'm essentially forming a linear combination here, 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 and then I'm summing up. So I get universal linear combination, which is potentially infinite. And then I have to add linear combination of number 1, which means constant times 1. Now, you would be tempted to write a0 here so that it fits. And that's not a bad idea, but you would pay for it later. And I'm not willing to pay that price. So I'm going to do a trick. A0 divided by 2. So for instance, if the right number here should be 6, then A0 will be 12. Okay, I put 12 for A0. 12 divided by 2 is 6, the number which I want to have there. And my question is, can I create such a trigonometric series so that when I sum it up in the usual way, I will get back the original function f? That's my question. And again, for the start, we want convergence which is local, pointwise. So we pick a number, and we look at how much is this sum, because when you put some constant for t, then this becomes a series of real numbers. We can find where it converges to, and we get some number. And we would like this number to agree with this number, Okay? But then we also want to look at it globally. These are some sines and cosines. When you mix them up, you get some wavy shape. And we can look at partial sums. So I put some capital N here, and I get some shape, and I put n plus 1, and I get different shape, and n plus 2 different. You know, I take longer and longer polynomials, longer and longer sums, and I look at their pictures, and I would like to see those pictures approaching this picture, just like we had it in the animation. So that's my aim. And I can try to repeat the theory, and this is where it really becomes a story, because there's a lot of really good mathematics happening, which I'm going to skip entirely, and I'm going just to tell you what the outcome is. So if you assume that your function is so nice that you can actually express it using such a trigonometric series, that those coefficients ak are uniquely determined, just like for the Taylor polynomial. In other words, there is a unique candidate, and if it works, fine, and if it doesn't work, then it's pointless to try anything else. So let me show you the first slide. We have a function which is t-periodic. We determine the proper frequency, and we set up the series accordingly, and hopefully I have the same notation. Yes, I do. And if this series, if you look at it and evaluate it, if it gives you the function f, and the convergence is uniform everywhere on the whole real line, then there are formulas for the coefficients. Now, there is a reason why these coefficients look exactly this way, but that would interrupt my story, and it would become a mathematical course. So I'm going to show a little bonus at the end of this lecture, and I'm going to explain why this shape for the coefficients, why these formulas are actually right. But for now, let's just have a look at it. Let's have a look at coefficient ak. Coefficient ak tells you how much of a particular cosine you want in your decomposition, in your expansion. And to find it, you simply take this cosine, you multiply with f, and you integrate over interval 0t. So you're sort of like measuring function against exactly that cosine or sine that you want to see in your expansion. So if you want to know how many cosine omega t you have in your expansion, how important it is there, what weight does it have, then you simply take this cosine omega t multiplied by f and integrate over one period. Notice that everything in the integral is t-periodic. So you don't have to integrate over 0t. You can simply start at some a and integrate to a plus t. The integration range can be shifted to the right, to the left, any way we find it convenient. So that's the beauty of periodic functions. And similarly for bk, that's the coefficient which tells us how important those individual signs are. You find it by taking this particular sign, putting it into the integral with f, integrate. There's some constant in front of it. Again, in the bonus part at the end of the lecture, you will see what they're doing there. Okay? So these are the formulas, and because they make sort of sense, they're relatively easy to remember, but we don't have to worry about it. And now let's ask a good question. First of all, what does it do for us? Well, it actually creates a transformation. It doesn't have a name, but it's in fact a useful transformation. Let's go back to power series. You have a function. If you can expand it into a power series, then it creates a transformation. Function gets transformed into a sequence of coefficients. And we talked about it previously that such a transformation has interesting rules. For instance, let's say that you have two functions and you want to add them. Instead, you can expand both of them, look at those sequences, and add those sequences. So addition for functions is transformed into addition of sequences. Then we had, for instance, special rule for multiplication by a constant. We even had a special rule for derivative. So if you can expand your function, which means you can express it as a sequence of coefficients, then we know how the derivative looks like. So there are some handy rules, and it's not really difficult to find that similar rules actually apply to this interesting transformation. You have a function, and replace it with a sequence of coefficients, but now the sequence is slightly more complicated. You have this A0, then you have A1, B1, A2, B2, and so on. And again, the rules are really similar. For instance, you have linearity. So if you have another function, and you expand it, so let's say that I use now capitals. Capital A0, capital A1, capital B1, capital A2, capital B2, and so on. So now each function is described by its own sequence of coefficients. And if you want to add them, you simply add the sequences of coefficients. And there are more rules like that, but I'm not going to waste my time on them because this is not the transformation that we want. But we do want to look at it closer. First of all, notice that in order to get those coefficients ak and bk, you don't really need to know your function on the whole real line, because you are integrating over the interval 0t anyway, or some other shifted interval. So we can actually start with just a function on some basic interval, small interval, and that would be enough for our work. Let's say from here a to a plus t. I put some shape here. Let's say this one. And now, if you really need a periodic function, you can always take this basic shape and replicate it. This is no problem. So let's say that I emphasize this one so that we can see that it's really important. And now I will make some, shifts. Perhaps this is not a really good copy, but let's be charitable and pretend that I'm making really good copies of the basic shape, okay? And also here, of course. And so on. So once you have your function on a basic interval, on some segment, you can simply, replicating it, obtain a periodic function. And if you do some work with this periodic function, then of course it will be valid for a function also on this small interval. There is a mathematical way to express that you take your function on an interval and create a periodic function. This is called periodic extension. And typically, and this is not quite, there's a little abuse of notation, this periodic extension is given the same name as the original segment. But it works in applications. And the definition essentially says, if you want to know how much is the value, for instance over here, then you simply jump by t to the left or to the right, depending on your position. You jump by t several times. How many times? That's exactly the integer k in the formula. So k times by t, that's how you jump. And this brings you to the original segment, and there you read the value. Okay, so that's how easy it is. So that's the first important observation. We can start with just a function on an interval. The second important observation is that this transformation is formal. When we have a function which is integrable on interval AAT, then we can use this interval to integrate, and we can create coefficients ak, bk, just some numbers. We don't know whether they are working well or not. And then we can take these numbers ak, bk and create a trigonometric series out of it. So we get this baby, this object. And again, this is a formal object. We don't know whether it works. We don't even know whether this converges. This could be a divergent series, but we don't care. This is just a formal picture. So you have an f, your function, and from function f, you create coefficients, and normally we would just keep those, but here it's traditional to take those coefficients and use them to create a series that we don't know whether it works or not, but we have a series, it looks nice. And this is called Fourier series. Okay, so that's a formal definition. The Fourier series that we see there, it need not have anything to do, like in graphs or anything, with f. It's just formally created. And now, important question, do we actually get back the original function? So that's the next theorem. It doesn't have a name because it's not the strongest theorem. It's a theorem which I sort of created by putting together a few observations, few theorems, so that it's convenient. There are much stronger theorems, but this one is nice for practical use. You have a function which is integrable on some interval, so you extend it periodically, so you have something to work with, and you create Fourier series, which, as we know, is formal. But now, if your function is piecewise continuously differentiable, what does it mean? It essentially means that your graph, your function f, consists of chunks, and on each chunk it's continuous and differentiable, and the derivative is also continuous. Okay, so that's the assumption, which is not terribly strong. Many functions have the form that they come in pieces that are nice. So if your function is nice, then this Fourier series actually converges. It creates a new function. And what does this new function have to do with your original function? And the answer is, if your function f is continuous somewhere, then the series will give you exactly the same answer. So over here, on those segments, the Fourier series would give you back your function f. What happens at places where a function is not continuous? That's a good question. And for that, we need to read properly this highlighted line. It says that the Fourier series, if you sum it up at such a place, will give you the average of the left and right value. So you look at the value from the left, look at the value from the right, take the average, and this is what the series will give you. So you could think that the Fourier series is sort of like doing average of your function from the left and right. Here the average is simply the function, and here it will be the place in the middle. So this is actually good news because many functions, as I said, are like that, and for those functions, Fourier series will give you the original function, which is nice. If your function is continuous everywhere, then this convergence is actually uniform, which is the best you can get. So that's a very good news. Let's have a look at some examples. So I taught Maple to do Fourier series, Fourier coefficients, and I start with a function that looks like this. As you can see, it's defined on interval 0, 2. So that would be the basic shape. And for the purposes of Fourier transform, it's good to interpret it as a periodic extension. So you get something like this. It's a very nice shape. And you can notice immediately that this extended function is continuous everywhere. So we expect to see very nice convergence. Here we go. Just out of curiosity, this is the Fourier polynomial or trigonometric polynomial for this function of order 13, and you can see that it's all just cosines. There are no sines in the expansion. And this is not surprising. Cosines are even function. Sines are odd functions. Now this guy is even. That's an even function. It's symmetric with respect to the y-axis. And it sort of sounds natural that when you are trying to express an even function using this family, then you don't really have any use for odd functions, for the sines. You will just get cosines. So lots of things make sense. So the Fourier series will consist just of cosines, and we will look at some partial sums. What we see here in this picture is the dark blue curve. That's the basic shape. I didn't draw the replicating parts to remind us that essentially we just know the function on interval 0, 2. And the red curve, that's actually the first degree Fourier polynomial. So it's a partial sum which stops k equal to 1 and also starts at k equal to 1. Then there is the shift. And you can see that the fit is not too bad because that's a very simple problem. So to see something more interesting, let's have a look at animation. Here we are. And I intentionally didn't draw the original shape into it. And let's see what happens when we start increasing the cutoff point for our partial sum. And here we go. And you can see how nicely the Fourier polynomials approach the basic shape. This is beautiful because this is a beautiful function. Let's try something, let's say, slightly more challenging. This is the basic shape for the function square root of x minus x. It's such a hill. So let's have a look at it. And it's not symmetric on the interval 0, 1. So when we replicate it, it goes like that. Now this shape is no longer symmetric around the y-axis, so this is not an even function. So I actually expect to see some signs in the picture as well. But let's not worry about formulas. Let's have a look at what's happening. So the red curve is the first attempt. That's the Fourier polynomial of degree 1. So just sine and cosine and a constant. The first two levels in my list, so to speak. And it sort of got the general shape going. Well, okay, not bad. The gold curve, that's Fourier polynomial of degree 3. So we went all the way up here in our linear combination, which is not too many functions, but we already got a better fit. In the middle, it's quite okay. We are following the dark blue curve quite faithfully. Just around 1, it's not all that good, because there actually the curve has to do a sharp turn, which is not easy for continuous functions to replicate. See, all these functions, sine, cosines, they are continuous. So sharp bends are really hard for it. And this bend is much sharper than this one. Here it was 90 degrees, right angle. Here this is much less. So yeah, this is harder. The green curve, it does better, and that's a Fourier polynomial of degree 8, which is not all that bad. I mean, it's not all that high. That's a fairly low degree polynomial, and it does quite a good job. So again, let's have a look at animation. I am here. Let's see. This will take a while. And again, I have shown here a larger segment so that we can see how this periodic extension thing is happening. Because the sines and cosines, they don't know that our original function was just on the interval 0, 1. They see everything periodically. Here we go. And again, this periodic extension is continuous. So I actually expect to see decent approximations. Here we go. And this time we will just go to polynomial of degree 20. And you can see that already polynomials of degree 20 are replicating the shape quite well. Okay? So that's the good cases. Now let's try something more interesting. Function x, but only on the interval 0, 1. What happens when we let the Fourier series look at it? Well, the Fourier series imagines that everything is periodic, so it actually sees this. And so on. Now, this curve, this function, is no longer continuous. And because it's not continuous, we can expect trouble. Let's see. So in this picture, we can see dark blue. That's the original shape. And again, I didn't replicate. But we see that those Fourier polynomials are trying to replicate the shape. And this time, we can see that there is more trouble for those polynomials. Again, the red one, this just sort of has a general tendency, but it's not all that great. That's a polynomial of degree 1. The next one, the gold one, is again 3. And the green one is degree 8. And when we look at the straight line and compare it with those 3 polynomials, we can see that this time the approximation is not all that great. There is lots of oscillations happening, especially towards the ends over here. Now, this is actually to be expected. Remember, our polynomials, they are continuous. So imagine that they are a continuous function, and suddenly you are supposed to go from here to here on a very short amount of time, so to speak. So what do you do when you have to have a big jump? Well, you sort of prime yourself, okay? Before I make a big jump, I go the other way a little bit. And that's exactly what the Fourier series is doing. If it wants to jump down really quickly, then first it takes a deep breath, so to speak, then jumps down and then overshoots, because the situation is symmetric in a way. So this is what you can expect, and that's something that unfortunately cannot be cured. That's one of the basic features of the Fourier transform. Every time you have a jump in your function, the Fourier transform has to oscillate to make this big jump. So let me show you animation again. And there are several things that we can observe. First, notice that those jumps will not disappear. They will be always there. Over here, and over here, over here, over there. And the intensity or the amplitude of those jumps will be the same also. It will not be decreasing. That's the bad point. If the amplitude was decreasing, we wouldn't have to worry, but it's still large, even for large polynomials. You can see it there on the right, on the left. You always see those oscillations wildly going around the jumps. Now this time I'm actually going to a polynomial of degree 100, and you can still see those big oscillations. This is unpleasant, and this is unavoidable. This is called the Gibbs phenomenon, and it causes troubles because when you want to approximate your basic shape using Fourier series, you are not able to do it everywhere. You can approximate in the middle. This is no problem. You can notice that in the middle, the approximation of the straight line is reasonably good. But it's worse than it was before for the continuous functions. So, I mean, everything is worse when your function is not continuous, and the Gibbs phenomenon, that's particularly bad thing. Let's have a look at another example. This is a very interesting function. It looks like this. It goes from 0 to 1 over here, and then from 1 to 2 over here. And again, we can expect to see the Gibbs phenomenon. So let me just show you few basic polynomials. This time the degrees are 1, 5, and 13. I had to go to higher degrees because the approximation is not all that good. You can see that the polynomial of degree 13, which is green, still has troubles following those straight lines. So really, once you have jumps in your function, you are in for some unpleasant surprises. And when Maple is finished working, I can even show some animation. This will take a while, because I'm really asking a lot of my trusty computing system. Here we go. I just focused on this straight line, because whatever is happening here is repeated here and here and here and so on. And when you look at it, here we go. Again, I'm going all the way to 200. So we will see polynomials of degree 1, 2, 3, 4, 5, up to 200. And you will still see some troubles towards the end. So the Fourier series is really trying hard to, first of all, approximate the straight line, the segment, and then to make the jumps. And you can see nicely what I've been talking about. There's this area where the approximation is becoming sort of reasonable, and it's spreading out. It's getting wider and wider, but the ends, they are getting more and more narrow, but there's still the big oscillation, Gibbs phenomenon. Beautiful. This is essentially it. Doesn't get any worse. And I can illustrate some interesting features of Fourier series here. Let me start with this. If I replicate this basic shape, then it will be a function which is not odd and not even. So I can expect the Fourier series to feature both sines and cosines. But here is an interesting idea. Remember that I'm just interested in this interval. So if I mirror this picture, and I'll pretend that this is the new period, then the Fourier transform will just replicate this wider shape, and I will get a series which will feature only cosines, because this function now is even. So I get so-called cosine Fourier series. And then when I look at just this basic interval 0, 2, it will give me the proper answer. It will give me the proper shape. And notice that there will be no trouble here and no trouble here, because I have continuity, so it will be even nicer. So sometimes people prefer to have Fourier series just with cosines, and they do it using this trick. You do even extension. Or perhaps, if I prefer sine, I could take the basic shape, and I could duplicate it in such a way that it becomes odd, which means I have to duplicate it like that. And now this basic shape gets duplicated by the Fourier. How does it go? This way. And this way. And again, I apply the Fourier a series to it, and when I look at the interval 0, 2, I get Fourier series which features only sines, because this is now an odd function, and it gives me the right answer. Again, there will be no trouble here, because I have continuity, but there will be trouble here. I have discontinuity there. And in fact, you don't have to worry about it. When you look up my notes about Fourier series, you will find that there are actually special formulas which are very similar to the original coefficient formulas. So you just tweak those coefficient formulas a little bit, and you get your cosine or sine Fourier series. This is very convenient. But let me show you a few more tweaks. So we will erase the blackboard and see what happens. Here we see the substance of Fourier series, which reminds me, I still owe you an explanation. Remember, divided by 2, not very pleasant, looks weird. If we wanted the Fourier series to look like this, without division by 2, then the formula for AK would have two versions, a special version for A naught. And that would be inconvenient. So people put up with this inconvenience in exchange for having just one formula for all AKs. Okay? We will see it in a second in another setting. This is really a good idea. Let's play. In general, when you are expanding a function, then these coefficients are in fact answers to the following question. How much of this shape is in this function somehow included? How much of this shape is included in this function? And the same is true for Taylor expansion. How much of x squared, x cubed, is in your function? But here, sine and cosine, they have the same shape. It's the same wave, just squeezed, expanded. So a better question would be, how much of this particular frequency is in your function, or how important this frequency is for your function? And that's a good question, but this form is not very convenient because the same frequency is hiding at two places. But in electrical engineering, they have a really neat trick which allows you to take such a linear combination, and assuming that the frequency is the same, you can express it using just sine or cosine. I actually personally prefer cosine, but in books I noticed that they mostly prefer sine. So I will do it with sine. So instead of two functions, I have just one, which is nice. I have just one constant instead of two, which is also nice. K omega t, and here's the punishment, plus phi k. That's a shift. If you decide to use cosine, you will have a different shift, but AK will be the same. AK is the amplitude of this frequency, because now it's lumped together into one expression. So the importance of this frequency is determined by this number. By the way, this number is the square root of AK squared plus BK squared. This is called, if I replace this expression with this expression, an amplitude-phase form of Fourier series. I remember typing it. So here we go. It's the version with sine. As I said, I prefer cosine. It also works nicely. Why is it interesting? Very often, you are investigating data and you suspect that there is something periodic happening. In nature, nothing is truly periodic, because there are always some other influences which sort of distort the picture. So just imagine that you have a record of, let's say, daily temperatures, but you are measuring it, let's say, every 10 minutes. You have a computer set up with a thermometer. Every 10 minutes it puts a piece of data in the memory. Then you print it out and you get something like that. And it's definitely not going to be periodic. I mean, truly periodic. But you strongly suspect that there are some periodic events influencing the temperature. So what can you do? Well, you simply take this piece of data and you apply Fourier transform to it, this type of transform. And you don't have to really worry about sine or cosine because AK is common to both. You simply figure out these numbers. So from the time domain, this is called time domain. We are looking at things from the time point of view. You go to frequency domain. You look at frequencies. These are AKs. And in fact, they are telling you about k omega, about frequencies k omega. And some of them are large, and some of them are small. And the interpretation is fairly obvious. If some frequency has really large AK, then it's important in the signal. So for instance here, I definitely expect to see a strong influence of yearly seasons, summer, winter, summer, winter. So definitely, frequency corresponding to 1 year in my data will have really huge AK. Another big amplitude can be expected with daily frequency. Day, night, day, night. The temperatures are going up and down. So that's another frequency that you can expect here. But perhaps there will be some other ones that you didn't notice before. Perhaps there will be a huge frequency or important frequency connected with 11-year cycle. And perhaps you will see the ice ages and interglacial periods, things like that. So this is called frequency analysis. And as you can imagine, it's quite useful. It can be useful in many areas of natural sciences. So that's one of the good applications of Fourier series. But you don't do it in the original way. You use this special form. There is a specific type of a signal which appears a lot, and that's music. So imagine that you have recording, which is done in electronic way, digital recording of a song. So how do you store it? That's a good question. Sound, music, that's lots of frequencies, and they're in fact also changing in time. It's not just the same frequencies happening all the time. So what you do, you cut your song into chunks. For each chunk, you find the frequency analysis. You find important frequencies, less important frequencies. Using simple formulas, integration, but let's talk about it a little bit later. What next? Well, you could store those frequencies, but there's infinitely many of them, which is not a good idea. But high frequencies and low frequencies are not heard by humans. You can cross them out, and you get a relatively small number of frequencies that you have to remember. And then generating uniform frequencies is very easy for a computer. So you let the computer generate those frequencies, you multiply them by the amplitudes, you put them together, and you play it, and you get a song. But this is still too much information to store. It would work, but the files would be rather large. So what they noticed, they talked to people who are experts on hearing, and it turns out that if there is an important frequency which is really high, which is really strong in your signal, then the human ear does not really hear frequencies which are nearby. So you don't need to remember those either. So you go through the signal and you pick up really dominant frequencies and you drop everything which is around them. This has to be done a little bit carefully, and you can choose how aggressive you want to be on that. And you are left with relatively few frequencies. You compress them, and what you get is MP3. So next time you are listening to some MP3 song, you will know that you are in fact listening to Fourier series. Wow, nice, isn't it? So that's a nice real-life application of Fourier series. Anyway, this was practical. Now let's move to something which I don't see as very practical, but it's an important step. So I have my series, and I'm still, let's say, not exactly happy that every frequency is encoded twice, and I don't want to go this way for some reason. So I'll try something completely different. What is cosine? There are many answers to this question. Let me offer you one. E to I k omega t plus e to minus I k omega t over 2. That's cosine also. And of course there we have sine. E to I k omega t minus, that's the change, e to minus I k omega t divided by 2I, another change. Now this is unpleasant, because I would like to use common denominator, and also complex units in the denominator, they are frowned upon, not very popular. So I'm going to multiply it by minus I, and also here by minus I. I have to do it twice to cover up my crime. Of course, you know that trick. Why minus I? Because minus I times I is 1. Okay? So this is really nice. Now there is just 2 in the denominator, and you can rearrange it. You can put these two exponentials together, I k omega t, and what's left in front of them is ak, and now I have to remember, I multiplied. Minus I bk, then there is the other exponential, ak, minus and minus is plus ibk. And now I'm going to be tricky. E to I minus k omega t. So remember, k ranges from 1 to infinity, so positive integers. And for every positive integer, this gets transferred into two exponentials, one with the same positive integer and one with the negative integer, mirrored integer. So in fact, this series, with k ranges from through positive integers, becomes a series of exponentials, where k now ranges also through negative integers. And these numbers can be called ck. And this is c minus k, to be precise. C minus k corresponding to minus k. So we have an alternative. Our function, instead of being composed of cosines and sines, it can be actually composed of complex exponentials, I, k, omega t, with coefficient ck. K ranges through all integers, and here it needs a little bit of work to make it, rather checking than work, that it also fits for k equal to 0, no problem there. And what's perhaps most surprising, there is universal formula for ck. And I remember how it goes, because it essentially goes exactly the same way as the original formulas. There is a little change here, don't worry about it. Integral function, and now the component of my basis, which I want to weigh, in a way, is repeated. So here I put exponential and dt. And fortunately, that's not all. I have to put minus here. So it's not such a good picture after all when you compare this setting and this setting. If you want to know how much of cosine there is, you put cosine here. If you want to know how much sine is, you put sine here. If you want to know how much an exponential is important, you put it here and you change the sign. This is unpleasant, isn't it? In fact, it's not different. These two formulas are the same, but you have to look at it from, let's say, a higher point of view. Because this formula is, in fact, integral and so on, ft, and now I put the exponential exactly the way that I want it to be, and then I put complex conjugation. So this formula and this formula, they are exactly the same. And now here is exponential, and here is the same exponential. It does make sense. Here is cosine, and here is cosine. Here is sine, here is sine. And now everything fits. But cosine and sine are real functions, so I don't have to worry about complex conjugation. See? So when you are living in the world of complex things, then suddenly these formulas, they become exactly the way you want them to be. They follow the same pattern. But if you don't want to play with complex numbers, then you have these formulas. And actually, that's what you usually find in books, because they don't want to bother people with some complex conjugation. They just give them this formula and tell them, go ahead, use it. Okay? So that's the complex form. And again, I remember myself typing it. So complex form. Did I get it right? Yeah, I did get it right. Wonderful. You probably noticed that I'm not exactly fond of the complex form, and probably the main reason is that I find it hard to make a good story about the complex form of Fourier transform. You see, the original form is quite easy to explain to a relative layperson, because we are talking here about frequencies. I'm trying to take a signal, let's say sound, and compose it of frequencies. That's something believable. And frequencies, everybody can imagine. High frequencies, low frequencies, no problem. But here suddenly I'm composing a function of frequencies masked as exponentials, and some of those frequencies are negative. What is a negative frequency? I find it hard to make a good story about it. But it is a good starting point. Let's accept it, and let's say that it's actually nice because it's compact, mathematically compact, just one coefficient instead of two, so it does have some points going for it. Now, we are restricting ourselves to specific frequencies. There is the basic frequency omega, and then we are multiplying it by positive numbers or negative numbers or 0, whatever. And the reason why we are restricting ourselves is that the original function was periodic. So we needed those frequencies to fit. But what if we have a function which is not periodic at all, on some interval, or even on the whole real line. Now, if this function is not periodic, then perhaps there is still a chance to compose it out of different frequencies, but we no longer have to worry about those frequencies being special. So, in fact, our aim now is to compose our functions. Composition means sort of like addition. And how many frequencies? Well, infinitely many, but actually uncountably many, because any frequency will do. So I have to integrate between negative infinity and infinity. Notice we are passing from discrete summation to continuous integration. Then there will be coefficients, and they no longer depend on some k, but on the frequency that we are looking at. Then there will be just exponentials without k, because I'm now changing frequencies. I'm going through all possible frequencies. That's the difference. Here, k was changing and changing from one frequency to another, but I don't need it anymore. I'm changing through all possible frequencies using the omega and integration. So that's a continuous version of a Fourier series. Now, these C omegas, these are special coefficients, and they have the same meaning. C omega is large if the frequency omega is important for my function. And perhaps, continuing in this manner, C omega could be, perhaps, integral from 0 to t, but that doesn't quite make sense. So perhaps from negative infinity to infinity, perhaps, because my function can exist everywhere, ft. And now I copy this function. And we know that we should take complex conjugation, so I put minus here. And I put dt, because now we're sampling the function. We are looking at the function and playing it against our exponential. And there will be some constant here, or perhaps here. People have different opinions. You see, 1 over t could also appear over here, if you want. It's up to personal preference, essentially. So there could be something happening here and here. And depending what we put here, something else will appear here, and vice versa. These are interconnected. So this is the picture that I would sort of like to see. And it turns out that it does work. And this function c is special, because again, it passes information. We started with a function with so-called time domain. Time is the variable. So you have a signal, and you look at how it goes through time. And this transformation provides you with information about the importance of frequencies. But now this information is not discrete, but it's also another function, C omega. So it's a transformation which takes a function with time domain and changes it into another function with a frequency domain. A totally new function which, at the first sight, or visually, has nothing to do typically with the original function. Because this one is about time changes, and this one is about frequencies. And this is called Fourier transform. Transform because it changes one function into another. This is the transform, going from f to this function. And because it's a transform, we are no longer calling it c, but there is a different notation. So let me show you a slide. And we can see that when we have a function which is integrable on real line, then we define a Fourier transform, which is the new function. That's what I'm calling c here, but they call it ff. So c omega is f, like that, omega. Or c is f, if you want. Or f hat, omega. That's another notation. There are many types of notation. People in different fields prefer different notations, and even mathematicians in different situations prefer different notations. This one is longer. This one is more convenient for quick calculations. For longer calculations, this one is perhaps slightly more handy. You will see it in the next lecture with a different transformation. So this is just to let you know what's happening. So when we have a function f, we can use this integral to get information about the frequencies. So that's transformation going one way. And of course, we would like to know whether we can go backwards and use those information about frequencies to get back to our original function. And the answer is, again, if your function is nice, if it's continuous, you will get it back. And if you have discontinuity, you will get the average. So there is a theorem about it. I don't really care much about it. So let's skip to the next part. We have a Fourier transform. It's a procedure which takes functions which depend on time, and it changes them, or this notation, into frequency functions. And this transformation has some rules, grammar rules and dictionary. That's what you need. People in applications very often do not really worry that much about mathematical background. They just learn the rules and they apply them. And this is getting us to the place where we wanted to be from the very start, because this is a differential equations course. So let's have a look at a differential equation. Y derivative plus 5y is e to x. Why not? Nice differential equation. Well. This is an equation which takes place in this world. I'm using x here, but x or t doesn't matter. I imagine that this is time. On the right, there is a specific function, this one. On the left, there is another function which is actually the same. It just looks different, but it's the same. Different label. So I can imagine that this point has two labels. Now, if I send over to this other world using Fourier transform both labels, I should end up at the same place, because the only difference is the labels, but the location is the same. So if I apply Fourier here, and if I apply Fourier here, the outcomes should be again the same. You can see why this notation is useful. Otherwise, I would have to be drawing huge heads. Perhaps I will later on. Okay, now on the right, I just need to find Fourier transform of the exponential. So I will use the head notation. Why not? On the left, I'm applying Fourier transform to some combination of functions, and perhaps I will find some rule for it in the grammar part. Grammar, the very first rule says Fourier transform is linear. Wow, beautiful. Linear transformation, that's what we love. So I'm going to apply Fourier transform to my derivative plus 5 times, and I'm applying Fourier transform to y. So far, so good. Now, Fourier transform, when I apply it to y, I have some function here which is solving my equation, hopefully. So when I send it over, it will be just another function. I don't know what it is, but I can give it a name. I think y hat is a good name. So 5 times y hat is e to x hat. Okay, what is the Fourier transform of derivative? There must be a rule about it. Oh, here it is. Lower right line. It says if you want to find Fourier transform of derivative of f, you put complex unit, you put omega, and then you transform the original function itself. So I'm transforming, let me write it, I'm transforming y. That's the rule for the derivative. And now I can pass to y hat. And you can notice that on the left, there is no derivative left. So my equation got transformed into this other world. Here it was a differential equation. Here it is not a differential equation. It's an algebraic equation. I can solve it easily. I can factor out y hat, because it's some function. I don't know which one. And notice that now in this world, omega is the variable. So if you want, you can imagine it like that. Now it makes more sense. And then I solve it for y hat. So I divide by this, I omega plus 5. And then I will try to transform back using most likely dictionary. So now at this moment, we would really need to know what is the transformation of e to x. And we would get some function with omega. And this would come here, and here, and here. Okay? So what function with omega is the transform of e to x? Okay, here is e to x. Where does it go? Well, let's have a look at dictionary. We are looking for e to x, and we do not see it. That's unpleasant. That's unpleasant. That's unpleasant. Well, I see Fourier transform of exponential, which is complex. But I don't see transformation of exponential, which is real. This is highly unpleasant, isn't it? Well, there is transformation, but you cannot express it with a nice expression. That's the problem. So if you are trying to transform the usual exponential, you will get some beast over here, and that's where it all breaks down. So essentially, in principle, the Fourier transform does change differential equations into algebraic equations. This is the good news. The bad news is that the dictionary is not very practical. It's unusable for differential equations in real life, in the real world. And also the grammar is not all that friendly because there are those complex units jumping out all over the place. So in principle, this is not a bad idea. But in practice, it doesn't work for ordinary differential equations. In other words, for this course. And that's exactly, going back to how I started this lecture, that's why this transformation is not the one that we want in this course. And that could be the end. However, a few notes. First of all, this is not such a big problem when it comes to solving differential equation, partial differential equations, because these are much, much tougher, and they are so tough that people are happy even for this help. So the Fourier transform is actually used when solving certain types of partial differential equations, which is way beyond the topic of this course. But it is a useful transformation. And in fact, it was invented essentially to help in solving differential equations a few hundred years ago. So this was a useful tool. The second important note is that this whole idea of taking signal that depends on time and finding information about frequencies, this is very important in signal processing, because when you take your signal and you change it into a frequency domain, you can start playing with it. So a lot of signal processing is done using Fourier transform. For instance, let's say that you have some song which was recorded and re-recorded and re-recorded. And when you do stuff like that, you get white noise in it. And white noise is high frequency sound. So what can you do? You take your recording, you change it into Fourier transform, you cut away high frequencies and you change it back, and the noise is gone. So there are filters for sound, which essentially work with Fourier transform. So it's very important. It's also important for data processing. For instance, let me give you a simple example. Sometimes people have to go for magnetic resonance imaging in hospitals, and to process the data, people use Fourier transform. Let me show you another, let's say, curious example. In the, I think, 1990s, FBI decided to digitalize its fingerprint collection. Now with fingerprints, it's important that they are somehow stored in such a way that you can search them efficiently. And imagine that you have fingerprints from 1 million people and you get new fingerprint and you want to find it. So going through 1 million cards and comparing pictures, this is impossible. So what they do, they are not really looking at the whole fingerprint and the whole picture, but they identify critical locations. So typical fingerprint has like islands, like that. And perhaps the better idea is to call them rings on the water. So imagine that you have thrown 3 stones into the water, and of course the water ripples and makes those circles spreading around. So if you want to identify a fingerprint, you just find those prominent features, and you say, okay, there is 5 of them, and they have this location. And if your fingerprint collection is smart, it is actually organized by prominent features. Now, when FBI wanted to digitalize, they of course asked people for some ideas. And the idea which won, which was used, is actually based on Fourier transform or Fourier series. It's interconnected. Because, if you remember, Fourier transform is essentially trying to compose signals out of sines and cosines, when I'm going back to the original idea. So you have waves. And you're using those waves to put together some signal, to create, to shape some signal. Now, there is a two-dimensional equivalent. You can really imagine that you have water rippling, so you have those concentric circles going up and down. And let's say that you have many of them with different frequencies, and you can try to use them to compose your signal. So the idea is not clear anymore because we are jumping to 2 dimensions, things like that. But the whole point is that when you are storing fingerprints using this idea, then again you get some information about importance of individual waves on the water, so to speak, or circles on the water. So some circles on the water are less important, some are more important. So that's a very efficient way to store fingerprints, which really are just a combination of those rings on the water. And moreover, it's really easy to search in such a database, because when you have a new fingerprint, you just change it into the Fourier coefficients, and then you're looking for a match for fingerprints with huge coefficients in those locations. So this is an extremely efficient way to store fingerprints, and it's again Fourier transform. So Fourier transform is around many places around us. I mean, you have it when you are listening to MP3, you have it when you are being fingerprinted, perhaps not that often. I think most people listen to music more often than they are fingerprinted. Perhaps you go to hospital for a magnetic resonance scan. I mean, this is really something very useful. And it's so useful that people started to worry about being able to do it efficiently. Because to do the Fourier transform, you would have to find infinitely many coefficients, which is not all that great. And to find them, we'd have to integrate from negative infinity to infinity. So what people did, they started with this idea, and they passed to a digitalized version, which essentially brought them back to this version. And for the integral, they used numerical integration. And there is a scheme which is extremely efficient. If you try to do it in the usual numerical integration way, you will end up having to do a lot of work. But there is an ingenious way how to reorganize the work so that it can be done in a short, let's say you need much less computations compared to the direct calculation. So there are big savings if you do it the smart way, which is called fast Fourier transform, FFT. And there are even dedicated microchips, they just do FFT. So it seems that this is really important, Fourier transform. And that's why I wanted to talk about it. That's one of the reasons. And the second reason is, let's go back to our example. This is really a neat idea. From derivatives, we pass to algebra. The only problem is that there are those complex units which are causing troubles here in the grammar. And in fact, they're also causing trouble in the dictionary. So in the next lecture, we will start by asking ourselves a very simple question. Can we do it without complex units? And we will see. So that's it for the story about Fourier transform. And if you're curious about some things which I hinted at, you can stay for the bonus part. Otherwise, see you next time. To start our bonus, we will go to linear algebra. Remember, you have a vector space, and in this vector space, you have some vectors that are linearly independent. You can imagine that it's a basis. So let's call them V1, V2, V3, and so on. I don't know how many of them, perhaps infinitely many. Now, typically, these would not be the basis of the whole V, but the basis of some subspace. They generate some subspace. And when we have a vector, some vector U, we, of course, aim to express it as a linear combination of these basic vectors. So U would be a vector from the subspace generated by these VIs. Good question. Where do we get those AKs? And here we really, if we imagine the Euclidean space, have the natural interpretation that AK tells us how much of a vector U lies in the direction VK. Okay? This is true in linear algebra for finite sums. But there is also a special theory where the basis allows for infinite sums for series. And then we can have infinite series, interpretation stays the same. Now, for, let's say, a slightly more useful answer, we have to go to the special case, special type of space, when we have inner product, which is exactly the case for the Euclidean space. But it's also the case for, let's say, more abstract, more general cases. Now, typically, we would call it U.V in the Euclidean space. But in more advanced mathematics, people actually prefer a slightly different notation, u comma v. Now, what is the interpretation? Well, this inner product is large if the direction v is very important for the vector u. So, here is the basic direction v, and the vector u could be somehow like that. So v is very important for it, and therefore, when you are forming the linear combination, this particular direction v should have a large coefficient. Now that's an interesting correspondence, large, large over here. By the way, it could be large and negative if the vector u goes in the opposite direction, or in the merit direction, like that. Here is negative v. Okay? That's just for the sake of completeness. This dot product could be small. If this basic direction v is used by u only a little bit. So only this much of the direction v is used in the vector u. The other direction is used much more. And of course, the extreme case, when the dot product or inner product is 0, it means that u is perpendicular to v. So I can write it like that. U is perpendicular to v. Now, this suggests that the inner product is exactly the right candidate for our coefficients when we are decomposing. For that, let's make an assumption that this base is orthogonal. What does it mean? It means that those vectors in the basis or in the basic sequence are mutually orthogonal, exactly like that. So vi is perpendicular to vj when I is different from j. That's the condition. And if this condition is satisfied, then we have a formula for a case. The formula for a case reads, it's the inner product of u with vk. So we're learning how much of u is in the direction of vk, or vice versa, how much is this direction important for u. But then we have to take into account that vk can have different magnitudes. So here we have to divide by the magnitude of vk squared. And in the inner product world, this actually translates to another form. The norm squared is the same as the inner product between vk and vk. This is sort of like a linear algebra review. And by a remarkable coincidence, exactly the same formulas are used when we do projections. So when we have some vectors, let's say v1, v2, and they form a plane, and we take some vector u which is not exactly there, but we want to find a projection, which means the nearest approximation in this flat world, then the coefficients are exactly done using the inner product. So that's a general linear algebra theory, here with perhaps a little bit of Hilbert spaces, things like that. Now, good question. We don't have abstract vectors, we have functions. So can this be somehow applied to the world of functions? Let's say functions on some interval I. So you have interval I, and here we have all kinds of functions. F, G, H, whatever. Lots of functions. Some of them may be discontinuous. Just to make sure that people remember that there are some functions which are not continuous, let me add another picture. This is still too nice. Ugly functions too. Now, could we introduce inner product into our world of functions? That's a good question. And the answer is, well, there is a way which is actually useful. Let's have a look at it. Inner product of two functions, f and g, can be defined as follows. You integrate over the interval I, ft times gt, complex conjugation dt. This formula satisfies all the properties which are required for something to be an inner product. So that's the first good news. And the second good news is that this formula actually is useful. It applies to real-life problems and it provides the right answers. So this is the good way to do inner product. Just out of curiosity, how much is the norm of a function. If I square it, it would be inner product of the function with itself. So if I take a square root, it would be square root of integral inner product of the function with itself. But this is nothing else but square root integral, and this is the magnitude of the function squared, dt. Does it make sense? Well, typically, when you say that a function is large, it means it has large values. And if it has large values, then these numbers are large, you integrate them, which means you sort of sum them up, and then you take square root. Square root and the square, they sort of like cancel each other. So you're essentially summing up how large the function values are. So it does make sense. The functions which have large values have large, this number. And the functions which have small values, they have this number small. Yeah, so it does send the right message. If your functions are real, you don't have to worry about complex conjugation, which is a bonus. But this is a general point of view. So after some work in a field which is called function theory, it is confirmed that this is actually a good way to run things in the world of functions. And now in this world of functions, we'll look at a specific sequence of interesting functions, of special functions. These will be the VIs. And of course, as you can expect, it will be the function 1, and then it will be the functions cosine k omega t and sine k omega t, where k ranges through natural numbers. And to make sure that we know what we are talking about, omega is positive and is fixed. That's the basic frequency. Can I apply this theory to my functions? Well, for that to work, they would need to form an orthogonal system. They would need to be mutually perpendicular. Just out of curiosity, are these guys linearly independent in the linear algebra sense? And the answer is definitely yes. For instance, you cannot take some sines and cosines and just add them up and get constant function 1. That's impossible. That's because the frequencies are restricted. When you play with it a little bit, you will see. And similarly, when you take some sine or some cosine with a specific frequency, you cannot compose it using the other guys, using a finite number of the other guys. So this set is linearly independent, and therefore it forms a basis of a specific subspace in the world of functions. And now I want to take some function and project it onto this space. I want to express it as a combination. In order to be able to use these formulas, that basis would have to be orthogonal, which means that these guys would have to be perpendicular to each other in the sense of this inner product. So we have to look at the integral from 0 to t, cosine k omega t, sine, let's say, L omega t. One guy from this family, one guy from that family, dt. And it's not difficult to show that it's 0, so they are perpendicular as vectors. We should also take two guys from this family and measure them against each other. Cosine k omega t, cosine L omega t, dt. And now, this is where it gets interesting. If k is different from L, then these are like two different members of the family. These are two different vectors. So they should be orthogonal. Is that true? The answer is yes. So here the answer is 0 when k is different from L. Now, what do we have when k is equal to L? When k is equal to L, then in fact we are asking for the magnitude. Or over here, for this number that we need for the coefficient. That's nice. So, how much is it? And this is where it gets tricky. It's t over 2 if k is the same as L is at least 1, and it's t if k is equal to L is 0. That's the special zeroth case. How do I know? Well, if k and l are equal to 0, then we are integrating 1 times 1, which is 1. We are integrating 1 over this interval, which is t. That's why the 0th term is special. And of course, we should check on the signs. Sine k omega t, sine l omega t dt is 0 when k is different from l. So again, if I take two different guys from this family, they are perpendicular. And if I take the same guy against itself, I actually learn the magnitude of this function in the vector space, in this sense. This is something that has to be calculated, but it's not totally difficult. It can be done using trig identities. So 1-2 pages of calculations and it's done. Okay? So this is quite okay. And once we do this calculation, we know that our system is orthogonal, and therefore we know that when we are doing the Fourier series or the Fourier expansion, when we are trying to express given function as a combination of cosines and sines, that we can use this particular formula. So let's have a look how this particular formula works, let's say for b, for sine, because then we don't have this trouble with 0 and non-zero. So how does it apply to the coefficient in front of the sine, bk? Well, we should divide by the norm of the vector squared. What is the norm of the vector? Norm of the vector is a square root of the inner product. So what we have to do, we take this. When we square root it, it will become the norm. And then we square it again, and we get to t over 2. T over 2. So far, so good. On the top of the formula, we should take inner product of our vector, which we are trying to decompose. That's our function ft. Against the vector that we want to project into, against our sine. And the formula for the inner product says we should take sine k omega t, take the complex conjugation dt, and integrate between 0 and t. That's the formula for bk, which follows from general theory of linear algebra or perhaps Hilbert spaces. And you just play with it a little bit. So we move t over 2 up, it becomes 2 over t, integral 0 to t, ft, we drop the complex conjugation, and we have exactly the formula which hopefully, yes, here it is. So we essentially proved where these formulas come from based on very general theory. And that's it. Happy end. See you next time. Each function is described by its own sequence of coefficients, and if you want to add them, you simply add the sequences of coefficients. So addition here, addition in this world, they are the same operations, essentially. If you want to multiply this one by 13, you just multiply all the coefficients by 13, and so on. And if you want to multiply this by 13, then you can instead, if you want to add them, you simply add those two sequences. So in fact, the operation of addition transforms from the world of functions to the world of sequences. And similarly, for instance, if you want to multiply f by 13, you just multiply the sequence by 13. It comes to the same thing. Now, it's interesting to note that this transformation is in a way formal. No. For the last time, hopefully. So if you want to add these two guys, you just add the two sequences. This means that the operation of addition in this world of functions so if you want to add these two functions, you just add the sequences. So instead of adding functions f and g, we can simply add the two sequences, and it will lead to the same outcome. And the second important observation is that when you are calculating those coefficients, you can shift the interval. So instead of adding functions f and g, we can just add the two sequences. And if the function is continuous, we even get uniform continuity, uniform convergence, which is great. Okay. Am I happy with this? I'm not quite sure. Should I try it again? That's a good question. Okay. So instead of adding the functions, you can simply add the sequences. In other words, the operation of addition transforms to operation... no. So instead of adding the numbers, you can add the sequences. No, blah, blah, blah. I'm hopeless. I'm hopeless. And I lost my papers. I left them there. Oh, shit. Oh, no. Oh, well. And so instead of adding the two functions, we can add the two sequences. In other words, the operation of addition in the world of functions transforms into operation of addition in the world of sequences.